In the third part of the 777 flight control series, we will operate the rudder of the aircraft. The rudder provides yaw control, and can be operated using 3 different inputs: the rudder pedals, autopilot command, and the rudder trim system. Let's start with the rudder pedals. The pedals move on their pivot axis, with the help of pedal arms. Control rods connected to the arms rotate the jackshaft assembly. The jackshafts move the control rods, connected to the left and right shaft assembly. The rods move to rotate the shaft assemblies. The 2 set of pedals are connected with a bus rod. The bus rod ensures when one pilot operates the pedals, the other side has the same movement. This gives the other pilot an indication of pedal position. The rudder feel and centering mechanism provides the feel force to the rudder pedals. As the pedals travel further, it gets harder to push. And once the pedals are released, the spring force returns the pedal back to neutral. Now let's see how pedal movement results in rudder deflection. The shaft assembly rotation is picked up by the position transducers. The transducers, in proportion to the pedal movement, send signal to the actuator control electronics. The ACE relays the signal to the primary flight computer for rudder movement calculation. The PFC returns the final signal to operate the rudder. The ACE sends control signal to the 3 rudder power control units in the vertical stabilizer of the aircraft. The PCUs are hydraulic actuators and use different hydraulic systems for redundancy. The 777 has a rudder tab connected to the rudder. When the PCU actuators move the rudder, the tab moves along with it. But the tab also has a mechanical rod connections, which deflect them further ahead of the rudder displacement. The mechanical connection is rigged to move the tab twice the distance of the rudder movement. By slipping further into the airstream, the tab increases the overall effectiveness of the rudder. Position transducers on the PCU send the rudder position to the primary flight computers. This allows the computers to control the rudder with precision. Now let's look at the autopilot rudder control. The autopilot function is similar to the pitch command, as seen in the previous elevator chapter. Autopilot computer sends a yaw command to the primary flight computer. The PFC commands the ACE to deflect the rudder to meet the autopilot demand. At the same time, the PFC commands the autopilot computer to backdrive the rudder pedals. The autopilot computer engages the back drive actuator and runs the motor to match the rudder pedals to the current rudder position. Back-driven pedals informs the pilot of an autopilot rudder deflection. Once the autopilot command is over, the actuator clutch is released and the pedals return to neutral. Finally, let's see the rudder trim control. The rudder trim switch in the cockpit is used for trimming the rudder. The trim switch has to be rotated for a nose left or a nose right command. Let's rotate for a maximum nose left trim. The trim switch sends a signal to the primary flight computer through the ACE. The PFC, in proportion to the trim requested, controls the rudder trim actuator connected to the feel and centering mechanism. The actuator moves the rudder pedals. The movement results in deflection of the rudder, just like manual control. The actuator will now hold the rudder in its new trim state. Pressing the trim cancel switch sends signal to the PFC to return the rudder back to 0 degrees. Next chapter of the flight control series will be Aileron and Flaperon control. Thanks for watching. Previously, in the 777 flight control series, we covered all the flight controls in the tail section of the aircraft. Now it's time to explore the control surfaces on the wings. For this chapter we have selected the 2 roll control surfaces: the ailerons and the flaperons. Flaperons serve 2 purposes on the aircraft. During a roll command, the flaperons act as inboard ailerons, and during flap extension, they droop to assist the main flaps. In this chapter, we will understand the roll function. 3 inputs can operate the surfaces: control wheels, the autopilot command, and the aileron trim function. Let's start with the control wheels. Control wheels are used to give a left or right roll command. When rotated, the wheels move the control cables. The cable movement rotates the cable drums. The drums rotate the left and right shaft assemblies. The two shaft assemblies are connected, so the rotation of wheel on one side transfers the movement to the other wheel. This ensures both the pilots have indication of aircraft roll command. Feel and centering mechanism provides the spring force to the control wheels. The further it is rotated, the harder it gets. And once the wheels are released, the spring returns them to the neutral position. Let's look at the aileron and flaperon deflection, due to control wheel rotation. The wheel position is picked up by the position transducers, and sent to the actuator control electronics. The ACE relays the signal to the primary flight computer, to calculate the movement. The PFC instructs the direction and deflection positions, for all the 4 surfaces. The ACE will now operate 8 power control units, 2 for each surface. PCUs are electrically controlled hydraulic actuators, and use different hydraulic system of the aircraft, for redundancy. For a left roll command, the flaperon and the aileron on the left wing are deflected upwards. The command signal for the right wing surfaces is inverted. The flaperon and the aileron on the right wing are deflected downwards. Position transducers on the PCUs indicate the surface position to the computer. This allows the computers to move the control surfaces with precision. Moving on to the autopilot roll control. The autopilot computer gives a roll command to the primary flight computer. The PFC instructs the ACE to move the control surfaces to meet the autopilot demand. At the same time, PFC instructs the autopilot computer to backdrive the control wheels. The autopilot computer now engages the backdrive actuators, runs the motors, and rotates the control wheel to match the control surface deflection. This gives indication to the pilots of an autopilot roll change. Once the command is over, the actuators are disengaged, and the control wheels return to neutral. Finally, the aileron trim function. Aileron trim measurement is different to pitch and rudder trim. During a pitch trim command, single control surface deflects, that is the horizontal stabilizer. Therefore, it is easy for the indicator to represent one unit as 1 degree of horizontal stabilizer movement. Likewise, during rudder trim, the rudder is the single surface that deflects, and 1 trim unit indicates 1 degree of rudder movement. But trimming the aircraft in roll axis will result in movement of 4 control surfaces. That is the 2 flaperons and the 2 ailerons. They also deflect in varying degrees and opposite directions. Therefore, for simplification, the aileron trim is in proportion to the control wheel movement and not the control surfaces. 1 unit of aileron trim indicates 5 degrees of control wheel movement. So let's trim for 20 degrees left control wheel position. When the trim switch is used, it sends a signal to the primary flight computer to rotate the control wheels. The PFC acknowledges and operates the aileron trim actuator. The control wheels are rotated until the switch is released. The wheel rotation results in flaperon and aileron deflection, just like a manual input. The trim actuator will now hold the control wheels in the trimmed state until a new trim input is given by using the switch again. The next chapter of the flight control series will be the spoilers. Thanks for watching.